We're going to begin chapter 3 now, and chapter 3 is about both finite groups and subgroups. So in this video, we're going to explore just some of the terminology and notation that you need to be successful. The first thing we need to understand is the difference between finite and infinite groups. Now, obviously, the terms finite and infinite aren't new to us. We know that finite means countable, and infinite obviously means not countable, or that it continues forever. So let's take a look at a couple of the groups to know, and I've done my best to include as many of the groups to know as I could. We first studied these back in chapter 2. But I wanted to include them here again because these are the groups we're going to see over and over. So let's take a look first at the group of Z3. Now notice here I did write Z3 under addition, but typically again you're just going to see this as Z3 and modular addition is implied. So if you forgot about all of that, go back to chapter 2. I have a great table at the end of the 2.1 video that has all of the groups to know and their associated operations. But again, looking at Z3, this is modular arithmetic for mod 3. So the elements of the group are 0, 1, and 2. So this is a finite group because it's countable. There are 3 elements in the set, 0, 1, and 2. And then if I would add 1 and 2, I would get 3, but 3 is actually 0 mod 3, and that's why there's only 3 elements in the group. Whereas if I look at the group of all integers under addition, well, how many elements are there? There's 1, 2, 3, 4, and really this goes on forever and ever and ever. So how many elements? There are an infinite amount of elements, and therefore we would say the order of Z3, and that's the notation we're going to use. It's like the absolute value bracket. So the order of the group Z3 is that there are 3 elements, whereas the order of the group of integers under addition, notice I didn't have to write addition up here, is infinite, an infinite number of elements. Now let's look at the difference between the order of a group and the order of an element. So we just talked about the order of a group. The order of a group is the number of elements of a group. But the order of an element, and I'm going to give you the official definition in just a second, but the order of an element isn't the number of elements in a group, but the number of times that we have to perform our operation to get back to the identity. So that's the basic idea. Now, I have it written a little more formally. The smallest positive integer n such that g to the n is equal to e, or ng is equal to 0 for additive notation. But what this is saying is just what I said before. We're saying how many times do I have to perform the operation associated with that group in order to get back to the identity for that group. So if it's multiplicative multiplicative notation, we're saying g to the n is equal to the identity. If it's additive notation, we're saying how many times do I have to add that, or obviously multiplication is just repeated addition, to get back to 0, which is typically the identity for additive notation. So before we explore U15, which I have on the table, and we'll go through that in detail as well, I want to talk really quickly about additive notation just so we make sure we're clear on the difference between the two. So if I'm looking at Z3, we've already talked about the fact that the order for Z3 is 3. Now, that's the order of the group, meaning how many elements are in the group. What were those elements? 0, 1, and 2. Now, if I wanted to look at the order of each element, let's look at the order of 0, the order of 1, and the order of 2. How do I do that? It all has to do with what the identity is. So for this additive group, the identity is 0. So how many times do I have to add 0 to get to 0? Well, just one time. I just need 1 0 to get to 0. Well, let's look at 1. So if I start with 1 and I add 1 to it, what do I get? I get 2. And if I add 1 to 2, what do I get? I get 3, which is actually 0. So how many elements, how many times do I have to add 1? How many 1s do I need to get back to 0? I need 3 1s. 1, 2, 3. Let's look at 2. 2 plus 2 is 4, but 4 mod 3 is actually 1. And then 1 plus 2 is 3, but 3 mod 3 is actually 0. So again, the order of the element 2 is 3. So now let's do the same for U15. So U15 is just another one of those special groups I wanted to make sure that we talked about. U15 is the group of elements less than 15 and relatively prime to 15. So I've listed those elements here. Obviously, for instance, 3 would not be an element because 3 does go into 15. 5 would not be an element because 5 goes into 15. Although 6 does not go into 15, 6 has a common factor of 3, and therefore that's why 6 wouldn't work. So hopefully we remember that. Here are the elements 1, 2, 4, 7, 8, 11, 13, 14. Now, the reason I wanted to show you this example is because the one I have written in green is obviously for the additive notation, whereas if we're looking at U15, we're talking about modular multiplication. So now, let me just switch colors there real quick. So now we're talking about multiplication, which means my identity in this case is 1. So again, if I have the element of 1, how many times do I need 1? To get back to 1, I just need 1 time. So, sorry, I should have pointed out, the order of the group is 8 because there are 8 elements in U15. Now we're going to look at each element and their orders. So the order of 1 is 1. Now the order of 2, notice what I've done here is I've listed under generate. So I wanted to make sure it was clear. We're saying this is 2 to the first, and this is 2 to the second, and this is 2 to the third, and this is 2 to the fourth, again, under mod 15. So 2 to the first was 2, 2 to the second was 4, 2 to the third was 8, 2 to the fourth is 16, but mod 15, that's 1. So notice the fourth time I get back to 1, and that is why my order of the element is 4. Now that one's pretty straightforward. I didn't have to do too much modular arithmetic. Now let's look at 7. So 7 to the first is 7. 7 squared is 49, right? But 49 mod 15 is 4. And then 7 to the third is 343, but again, we have to do mod 15. That gives me 13. And then 7 to the fourth is 2,401. That's when I get back to 1 mod 15. So remember, here we're looking at powers because it's multiplicative. So that's g to the n is equal to e. So you can feel free to look at the rest of those, what they generate. Obviously, I've done it ahead of time so I know that they're correct, but then these are the orders of each of those elements. Let's do a little bit of practice. This practice is going to help us to remember some of those special groups that we're going to see over and over that maybe we have looked at already or maybe we have not. We're also going to find the order of the group and the order of one specific element of each group. So we'll start with D4. D4, remember, is the dihedral group, and the dihedral group 4 is the elements of the symmetries of the actions of a square. So we're looking at not doing anything, rotating once, rotating twice, rotating 3 times, or reflecting, or rotating and reflecting, or rotating twice and reflecting, or rotating 3 times and reflecting. And again, you could call this R90 and R270 and so on, but I'm going to stick with this notation. So the order of the group is 8 because there are 8 elements. We can just count them up. So remember, this is the group order. And then we're going to look at a specific element. So this is going to be the element order. Now remember, the element order is the number of times we have to perform that action in order to get back to the identity. So now let's think about what R generates. So if I did R once, I would get R. If I did R twice, I would get R squared. If I did R 3 times, I would get R cubed. If I did R 4 times, I'm actually back to the identity. I'm rotating all the way back to the beginning. So the order of the element is 4. Now let's look at U20. We're familiar with U. We just looked at U15. The group itself is the elements that are less than 20 relatively prime to 20. So let's come up with those. 1, not 2, 3, not 4 or 5 or 6, 7, not 8, 9, not 10, 11, not 12, 13, not 14, 15, or 16, 17, not 18, and 19. So we have 8 elements that are less than 20 and relatively prime to 20. Now let's look at the element of 7. So I could have chosen any one of those elements. Remember, with U20, the operation is multiplication. So I'm looking at 7 to the first, which is just 7. Then I'm looking at 7 squared, which is actually 49. But if I'm looking at mod 20, that's 9 mod 20. And then I'm looking at 7 to the third. 7 to the third is 343, which is 3 mod 20. And then I look at 7 to the fourth, which is 2,401, but that is 1 mod 20. So how many times did I have to perform 7? 4 times. Now let's look at the general linear group. Remember, the general linear group, we're just talking about a matrix. This tells us that we're looking at a 2 by 2 matrix, and Z tells us that all of the entries are integers. So what are the elements? Well, I can't even write them all, right? Because we're going to have some integer here, oops, no commas, some integer here, some integer here, and some integer here. And we just know the only restriction is that the determinant cannot be 0. So how many different options do I have? Well, I have an infinite number of options. Well, what is the order of the element 1001? 1001 is certainly in the general linear group because 1 minus 0 is 1. So we don't have a determinant of 0. But how many times must I perform that to get back to the identity? Well, what's the identity of a 2 by 2 matrix? This is the identity. So the order of that specific element is 1. Lastly, let's look at Z12. Remember, when we're looking at Z, this is the operation of addition mod 12 in this case. So it's addition mod n, whatever n happens to be. So what are the group elements? 0, 1, 2, 3, all the way up to 11. So how many values is that? What is the order of the group? The order of the group is 12, 0 all the way to 11. The element of 4, remember, this is not multiplication, this is addition. So basically I'm saying 1 times 4, which is 4. And then 2 times 4, which is 8. And then 3 times 4, which is 12, but 12 is 0 mod 12. And therefore that's back to the identity because the identity in this case is 0. So the order of that specific element is 3. Our next 2 videos are dedicated to the study of subgroups. What makes a subgroup? How do we determine if a subset is a subgroup? But let's just lead into that by taking a look back at U15. U15, if you'll recall, was 1, 2, 4, 7, 8, 11, 13, 14, and that was under modular multiplication. And our question is, does the element 2, or does the set generated by the element 2, which was 2, 2 squared or 4, 2 cubed or 8, 2 to the 4th, which was back to the identity under mod 15, do those elements form a group? So notice each of those elements, 1, 2, 4, and 8, are elements of my original group. My question is, would that subset form a group? So we have to check the same information that we did when we checked for a group originally. Closure. So if I multiply any two elements of that set, do I get an element of that set? One way is to create the Cayley table, and it's pretty easy to do that. 1 times anything is itself. 2 times 2 is 4. 2 times 4 is 8. 2 times 8 is 16, which is 1. 4 times 2 is 8. 4 times 4 is 16, which is 1. 8 times 4 is going to be 2 mod 15. And then 8 times 2 is 1 mod 15. 8 times 4 is still 2 mod 15. 8 times 8 is 64, or 4 mod 15. So we can see that multiplying any values in the group does in fact give us another value from that group, 2, 4, 8, or 1. So closure is satisfied. Associativity, this is multiplication. Modular multiplication is associative, so I don't have to do a lot of work to check that, except to say that it's associative because multiplication is associative. The identity, is there an identity in the group? Well, the identity of U15 is 1, and the identity of my subgroup, still 1. 1 is in the subgroup. And does each element have an inverse? Well, we can see very clearly the inverse of 1 is 1. The inverse of 2 is 8, and the inverse of 4 is 4. So yes, these in fact do, these 4 elements do create a group, so they are considered a subgroup of U15. So what is the definition of a subgroup? If a subset H, so recall subset means the only elements of H are elements of G, they have to come from G, is itself a group under the operation of G. So we have only elements of G, same operation of G, same identity of G, and so forth. We say that H is a subgroup of G, and we denote it with the less than or equal to sign. If you want to say specifically, because technically you could have H and G as the exact same group, but if you want to say that there's at least one element of G that's not in H, then that is a proper subgroup, and then notice it's just the less than sign. Let's look at 2 examples. First, is the special linear group a subgroup of the general linear group? Well, what's the special linear group? Special linear group is any matrix where the determinant is equal to 1, and the general linear group is where the determinant is not equal to 0. Now, I don't have to do any checks on this one because we've already talked about the special linear group, and it is in fact a group. So is it a group? Yes. Does it have elements from the general linear group? Yes. So this, yes, is a subgroup. Now, I cheated a little bit because I didn't have to check any of the properties, but that's because we already knew that this was a group from our previous study. Let's look at Z4 as a subgroup of the group of integers under addition. So this is a group of including 0, 1, 2, and 3. And the operation is modular addition, so addition mod 4. And this is the group of all of the integers, 0, 1, 2, and all the negatives and so forth. And the operation is addition. So you might be tempted to say yes, but because these are not the same operation, In fact, this is not a subgroup. So even though these elements all come from Z, the operation is not the same, and therefore it cannot be a subgroup. Up next is subgroup tests.